In this video, I'm going to be talking about the second derivative, concavity, and points of inflection. So a graph that looks something like this is said to be concave up. A graph that looks something like this is said to be concave down. So concave up, this part of the graph in here, is where the slope is increasing. Concave up is the slope is increasing. But even more importantly than that, the second derivative of the graph in this place is always positive. F double prime of x is greater than 0. Second derivative is positive. The part of the graph in here that is concave down is where the slope is decreasing. But even more importantly for this discussion, this is where the second derivative is going to be negative or less than 0. So concave up, the second derivative is positive. Concave down, the second derivative is negative. Now, at the point where the concavity changes from being concave up to down, right here is what is referred to as the point of inflection, where it goes from concave up to concave down, or vice versa. It could be from where it's concave down to concave up. This would be the point of inflection right about in here where that concavity changes. The second derivative would be negative in here and would be positive in there. Now, the point of inflection is where the concavity changes, and also important for this discussion, that's where the second derivative is equal to 0, which kind of makes sense. If the concavity is negative in through this part of the graph, and then it changes to being positive in through here, there must be a point where it is actually 0, and that would be at the point of inflection. The second derivative, f prime of x, is equal to 0. So let's take a look at this graph right here. So in this graph, we have a graph that goes from being concave down, right? That means this is where you can't read this too well, but that's where the second derivative in through here, the second derivative is less than 0. And it's also concave down in through here. So the second derivative is also 0 in here, less than 0. And then it switches to being concave up in through here. So in through there, the second derivative is greater than 0 or positive. And then in these two spots right here and right here is where the second derivative is equal to 0, right there and right there. And so that's what we're going to be looking for in the rest of this video, is how do we find those points of inflection? So let's do an example. Given this function, find the coordinates of the point of inflection. So first thing we need to do is find the first derivative. And so the first derivative here will be 3x squared minus 12x. And that's the first derivative. The second derivative then will be 6x minus 12. Now we set that equal to 0 to get 6x equals 12 or x equals 2. So this is my point of inflection. This is the x value of the point of inflection. If you want to find the coordinates, that means we also need to find the y value. So we need to then find f of 2. So f of 2 would be 2 cubed minus 6 times 2 squared, which is 8 minus 4 times 6 is 24, or negative 16. Hope I'm doing my arithmetic correctly. So we get the point 2, negative 16. That is my point of inflection. Okay, in the next example, same thing. We first have to find the first derivative. And so the first derivative will be 4x cubed minus 3 times 4 is 12x squared. The second derivative will then be 12x squared minus 24x. And we want to set that equal to 0. So we see that we have common factors here. We can factor out a 12x. That will leave us with x minus 2 equals 0. And then we use the zero product property that you learned back in an algebra class. And we set both factors equal to 0 and solve for x. So we now have 2 points of inflection. So we have to find f of 0. And so that's going to be 0 to the 4th minus 4 times 0 cubed, which is 0. So the point when x is equal to 0, we get y is equal to 0. So that point is going to be 0, 0. And then we have to find f of 2. So that's going to be 2 to the 4th minus 4 times 2 cubed. 2 to the 4th is 16. 2 cubed is 8 times 4 is 32. So that is negative 16. And so my other point is going to be that value and that to give us 2, negative 16. And so we have 2 points of inflection. Now, what would a graph that looks like that possibly look like? It could look something like this, where we're concave down, and then we go concave up, and then we go maybe concave down again. So we would have 2 points of inflection, one right about in here, and one right about in there. And finally, this last example, find the coordinates of the point of inflection. So our first derivative is 2x minus 4. The second derivative is simply a constant, 2. All right, so it is a constant 2. So what exactly does that mean? Well, the important thing is that 2, this is positive, right? It's a positive 2. It's positive 2. And so the second derivative is always 2, therefore always positive, therefore it's always concave up. Remember that the graph where it's concave up, the second derivative is positive. Well, since this is always positive, it's always concave up. Well, what happens if we had a graph of a second derivative that was negative? What happens if f double prime of x is negative 30? Well, the important thing is here that it's negative 30. It's always going to be negative. Therefore, this graph is always concave down. Always concave down. In other words, there is no inflection point. There's no point of inflection. If your second derivative is always positive, or if it is always negative, if it's a constant, there's no point of inflection. And the concavity is always positive or always negative and never changes. All right, so that is concavity and points of inflection.